Assalamu alaikum. So, in the last part of the section relations, we have discussed this theorem. Says that we have a relation R on a set A, then R is an equivalence relation on set A, if and only if A is a subset of R, where, sorry, not the A, this delta is a subset of R, where this delta can be written as a set which contains all the order pairs of x comma x, where x is in A, kind of all the elements which are reflexive, and then R is equal to its inverse relation, and the composition of R is also a subset of R. Then R is an equivalence relation on a set A. Now, then we will talk about some examples, worked out examples, and then we will show them. So number one is, so we have Z10 and we will show that which of the following equivalence classes are equal. Which of the following equivalence classes are equal? Something more. The equivalence classes are 2, minus 5, 5, minus 8, 12, 15, minus 3, minus 3, 7, and 22. Solution. Now we know that to show that following are the equivalence classes, what we need to do is a simple exercise. So we note that two can be written as 2 plus 10, and that will be 12. So the equivalence class 2 and 12 are same, because 10 is a multiple of 2. Similarly, minus 8 can be written as minus 8 plus 10. That is also equals to 2. Similarly, 12 is 12 plus 10 will be 22. Then 12 will be equals to 12 plus 10, which is 22. Similarly, minus 5 will be equals to minus 5 plus 10, that is 5. which also be equals to 5 plus 10, which is 15, and minus 3 is minus 3 plus 10, which is 7. Also, 2 is not equals to the equivalence class of 5. 2 is not equals to the equivalence class of 7. And 5 is not equals to the equivalence class of 7. We can check these. Hence, now follows that the equal clauses are 2, 12, minus 8, 22, minus 5, 5, 15, and minus 3 is 7. Okay. Number 2 is let's consider a reflexive and transitive relation on a set S. Prove that the intersection of that relation with the inverse is an equivalence relation. So let R be a relation, be a reflexive and transitive relation on a set S. We need to prove that R in intersection with its inverse is an equivalence relation. And to prove that, we can think of a technique by which we can do that. We can take the order pairs from this relation and then show that that order pair lies in the inverse. And then that order pair lies in the intersection. And then similarly, we need to show, and that will make it reflexive. And then we can also take one order pair with 2 different elements from this relation. And then we can also say that order pair is also inside the inverse, and thus we need to show that the order pair other way around is also in the inverse and then in the relation, and that will show that it is transitive. Sorry, it is symmetric, and then we can follow the same technique to show that it's transitive. So let's do that. Now, since we know that R is a relation, then because of that, x comma x, the order pair x comma x will be in R for all the x inside the set S, comma, this R will also be inside the inverse for all x in S. Thus, this order pair is in the intersection for all x in S. Hence, the intersection of R and R inverse is reflexive. Remember, to show it is an equivalence relation, we need to show that the relation is reflexive, symmetric, and transitive. Now, we relate that x comma y is in R X comma Y is in R, inverse R intersection R inverse. We late that. That means then this X comma Y is in R, and X comma Y order pair is in R inverse, and thus Y comma X is also in R inverse, and Y comma X is also in R. So see, if you assume that there is an order pair X comma Y inside the intersection, and these two are straightforward. But if the R, this X comma Y is in the R and then in the inverse, then you can also write that by saying that if X goes to Y and X goes to Y in the inverse is also in inverse, then by the inverse, you can also say that Y goes to X. So you can do that. Okay. Therefore, this order pair Y comma X is in the intersection, which says, hence, this intersection is symmetric. Perfect. Now, suppose that there are two order pairs X comma Y and Y comma Z in the intersection. Then these order pairs will also lie in the relation and the inverse of the relation. Okay. Since hence R is transitive. Since R is transitive. Since R is transitive because it is given transitive, we know that Z comma X is inside R, and Z comma X comma Z is inside R inverse, which is also true. Thus, X comma Z in the intersection. Hence, R intersection R inverse is transitive. Hence, the intersection is an equivalence relation. Hence, the intersection of R into R with R inverse is an equivalence relation, because we have proved that this intersection is reflexive, symmetric, and transitive. Perfect. Now, let's say number 3, we have, so let's give an example of an equivalence relation on a set S. So we have a set, let's say 1, 2, 3 up to 8. Such that R has exactly 4 equivalence classes. Give an example of equivalence relation on the set such that R has exactly 4 equivalence classes. So maybe I should write that also. So give an example of an equivalence relation on the set, on this set. Okay. Solution. So we can try by looking at the elements inside the equivalence relation R. So let's say we have a relation R which has elements like this: 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8. And then you can also say 1, 2, 2, 1, 3, 4, 4, 3, 5, 6, 6, 5, 7, 8, and 8, 7. Okay. So we can define this relation is a simple one. So 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4, 5, 6, 7, 8. If you have another pen, so you can send this to every one like this. So 1 goes to 1, 2 goes to 2, and then everyone goes to itself in the first part, in the first instance. And then 1 goes to 2, 2 goes to 1. So one goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 3, and then 5 goes to 6, and then 6 goes to 5, and then 7 goes to 8, and 8 goes to 7. We can do that. Okay. Now, to show that which of the equivalence classes are there, we can say that there is equivalence class 1, which is similar to 2. There is equivalence class 3, which is similar to 4. And then there is equivalence class 5, which is similar to 6. And then the last one is equivalence class 7, which is similar to 8. Because of these order pairs, the equivalence class 1 and 2 are same, 3 and 4 are same, 5 and 6 are same, and then 7 and 8 are same. Perfect. Okay. Then Number 4 would be we have a set A 1, 2, 3, 4, 5, and we have a relation 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and then 1, 2, 2, 1, 4, 5, 5, 4. We need to show that R is an equivalence relation. To show that, what can we do? We can do that. We can assume that B is a set 1, 2. C is a set which is 3. And D is a set which is 4, 5. We can define a partition of the set B, C, D. We can say this P is a partition of the set A. And we also note that if X, Y belongs to A, then X, Y belongs to this relation R if and only if they are an X for some set X inside the partition, i.e. the relation R is induced by the partition P. By theorem 1.3.18, you can say by 18 R is an equivalence relation on A. R is an equivalence relation on A because the partition P contains all of the elements that are present in A. So, and the relation, and so all of the order pairs inside the relation, the elements inside all those order pairs somehow, like all of those elements lie in some of the sets of the partition. So that's why the partition induces a relation R, which is an equivalence relation, and that we have talked in theorem 1.3.18. Perfect. Let's talk about how can we do that for a set. So number 5 is we have a set X with elements 1 to 7. Then we have a partition which has subsets like 1, 2, 3, 1, 3, 5, 2, 6, and 4, 7. We need to list the elements of corresponding equivalence relation R on X induced by partition. List elements of the corresponding equivalence relation R on X induced by this partition. Remember, we need to look after these sets also. We need to talk about we need to take all those order pairs which can be present there. And to know that which order pairs can be present there, we have the definition that R will contain those elements from these sets X cross X such that A and B both belong to same set inside the partition, or element you can say, because these sets are elements inside the partition, element of P. This is the definition for the relation, and we can say that R contains 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7. Now there will be a scene like difference that you can see. One can go to 3, one can go to 5, 3 can go to 1, 3 can go to 5, and then these can have different relations in between them. So because this set have 3 elements, so we can generate more order pairs like 1, 3, 3, 1. We can generate 5, 1. Let's write before. We can generate 1, 5 and 5, 1. And 5, 1. We can also generate 3, 5 and 5, 3. Now we cannot do more for the first set inside the partition. Then for the second set, we can we do? We can do 2, 6, 6, 2. And then for the third set, we can do 4, 7, 7, 4. These are all the elements inside. These are all the order pairs inside the relation R. And this relation is induced by this partition P on a set X. Perfect. The last one. Number 6 says that we have a relation R on a set S. Let R be a relation on a set S. We need to prove the following conditions are equivalent. Prove following conditions are equivalent. Okay. Which conditions? Number 1, R is an equivalence relation on S. R is an equivalence relation on the set S. Number two, if it is equivalent, then we have the following conditions. Number two, R is reflexive. Reflexive, and for all A, B, C inside the set S, if A is R related to B and B is R related to C, then A is R related to C. Kind of a transitive property. Then we can show that, to prove that. Proof for solution. Now you can see one imply two. How? Because if we assume that one is true, then R is an equivalence relation on S, then this shows that two is true. Why? Because if R is an equivalence relation, it will be reflexive and it will surely follow the transitive property, which is this one. So we can write one implies two. Then we can suppose R is equivalence relation on S, then R is reflexive, and late ABC belongs to S, and we can suppose A is R related to B and B is R related to C, then transitive property of R implies that A is R related to C. Okay, so difference we need to show here. That was too easy. This would be too easy to show because it will follow that. The only thing we need to show here was the difference. C is RA. Okay. So now we can talk about implies that A is R related to C. Hence, if this is true, then CRA is also, C is also R related to A because there is because R is equivalence relation, so R is also symmetric because R is symmetric. So this is true for every element. So if you can write why this is true, because if A is R related to C, then C is R related to A because R is symmetric. So that's why this is true. And this shows that one implies two. This shows that number two is true. And then we can assume two is true and two imply one. So number two imply 1, and how to solve that. So we now know that we have all this information which is in 2. We just need to make sure that 1 is R is 1 is true. So to do that, now since R is reflexive, is given to be reflexive, and to show that R is an equivalence relation, we only need to show to take R is symmetric and transitive. We only need to check R is symmetric and transitive. For symmetry, suppose A is R related to B. Now, since R is reflexive, we have A is R related to A. Now, since we have A is R related to A and A is R related to B, B is R related to A by hypothesis. This shows that R is symmetric. Correct. For transitivity, suppose A is R related to B and A is R related to C, then by hypothesis, C is R related to A, which was given in the question. So since we have shown symmetry, that R is symmetric, CRA implies that A is R related to C, hence R is transitive. R is transitive, and consequently, R is an equivalence relation. On this set S. Perfect. We will end this section here, and I'll talk about the partially ordered sets. Good luck. Thank you.